there something like
Thermal energy. Ladies and gentlemen. Once upon a time, whether it was grade 8 or grade 9 or it should have been grade 8, it used to be part of grade 9, you would have been introduced to the kinetic molecular theory. Hands up if those words in that order is something you've heard of before. Kinetic molecular theory. Cool. Well enough that you can explain it. Hold on.
I heard it in chemistry, like something related to that.
Okay.
I don't have no
It shows up again in Chem 11. Connor, you want to try? What does the kinetic molecular theory state?
Thank you. Yeah, no, I passed.
Okay, cool. You could have just read it right off the thing here. The kinetic molecular theory states that all matter is made up of tiny particles, atoms or molecules. And I'm not going to go into the distinction between those two because you should have done it in either Chem or Science 9. These particles are always moving except at when? No. These particles, atoms or molecules that make up everything are always moving except at one particular state. No. But the definition of at rest is not at rest.
It's thermal, when they're like super cooled or whatever.
What is there you go. Thank you, Manuel.
Or something. What is it?
Okay, so absolute zero, in case we forget what it is defined to be 0 Kelvin. That's not okay. That's 0 degrees Kelvin, named after a dude, Kelvin, which is equivalent to minus 273 degrees Celsius. It's very cold. And that is defined to be absolute zero because you cannot get colder than that by definition of what thermal energy actually is. These particles are able to move. As you increase your temperature from minus 273 Celsius, these particles are going to start moving a bunch of different ways, well, 3 different ways specifically. What are the 3 ways these things can move? What are the 3 ways? Sorry? Actually, yes. We'll call that translational motion.
Thank you.
I know that when the particles start moving and hitting each other, like if they explode the thing.
Or it transfers. It's a transfer of energy. So translational motion. I mean, Connor called it bouncing, but bouncing is just translational motion in 2 directions. You're moving in a line. Particles are able to move within substances. How else are these things able to move? No. They don't through each other, they hit each other, bounce off each other. That's all translational. How else do particles move in substances?
They get excited.
No, but like how do they move? Like what are they doing to move? They're shaking. Shaking. We don't call it shaking, we call it vibration. And it doesn't happen the way we typically expect it to happen. What vibration or shaking looks like in a molecule is this. So this should be familiar to you, yes?
Yeah.
That's water. What vibration looks like in a molecule of water is these hydrogen bonds actually get longer or shorter as the hydrogens bounce closer or further from the oxygen atom in the water molecule.
That makes sense.
Okay, so that is what vibrational motion looks like. The other way these things happen, there's one more. We have the shaking, we have your bouncing, or translational and vibrational. One more kind of motion.
A question: the polarity of the molecules interfere in the vibration thing?
We're not dealing with polarity, that's chemistry. But yeah, so I can't comment on that. I'd have to go back and do some more reading before I can talk about that. Khalil, you got like 2 minutes, just a heads up. Tenjo, you said? Kind of. Not orbiting per se, but revolving, rotating. You've got rotational motion going on there.
Are we talking like this? Or like this.
Orbiting is going around. Rotational is spinning. Each type of movement has its own form of kinetic energy. We're not going to talk about these other forms of kinetic energy this year. You'll talk about oscillating and rotating. That might actually wait till first or second year university because that gets really complicated. Particles, therefore, can have several types of kinetic energy as well as potential energy. The potential energy comes from the intermolecular bonds that are present. So in water, you've got molecules of water that are attracted to each other. Because of their polarity, that's as much as I'm going to say about polarity. You've got oxygen, no, I'm going to say more. You have an oxygen that's partially negative. You've got hydrogens that are partially positive. And so these molecules are going to interact with other molecules. This creates a form of potential energy, chemical potential energy. A measurement of the amount of energy in a substance is what we call thermal energy. Thermal energy is, by definition, the total energy of all molecules in an object. So that total energy is kinetic and potential. And so the concept then, it's related to the concept of heat. Heat is the transfer of this energy. From one object to another. So, if I have a really hot object, we know it's hot because it's red. And you've got a blue object. I'm using blue to represent coldness, which technically is a little bit weird because red flames are cooler than blue flames, but humor me. Which way is the energy going to flow here? From which object to which object? It's going to flow from hot to cold. A hot object has more thermal energy, so it is going to transfer energy from itself to the colder object. Yeah.
One example would be like if you had like a pop bottle that you with some water in it or something and you heated it up and then you take it off like immediately and put it in like a cold bucket of water and it snaps together. Would that be an example?
That's an example of an application of some of this stuff, but that's more complicated than just this. Yeah.
So that explains like why when you touch something that is really hot, you feel pain because there is a lot of energy transferred in a short period of time.
Yes.
You can feel it, the transition.
Yes. Yes. That is why burning hurts. When does the energy stop flowing?
When the body reaches the same temperature as the induction.
Yes. Energy flows until the objects reach the same temperature. We have a name for this state. When these objects are at the same temperature, we say they are in thermal equilibrium. And we've got one more definition for you here. Temperature is our last definition. Temperature is a lot more specific than thermal energy. Temperature is the average kinetic energy of all molecules in an object. So thermal energy is the total energy of all the molecules. You're adding them up. The average kinetic energy of all the molecules at temperature is already starting to restrict this definition. We're ignoring all potential energy when we talk about temperature. And we're not summing up the thermal energy. We're averaging it molecule to molecule, which is fundamentally different. So which object is going to have more thermal energy? A lit match or an iceberg? A standard iceberg. It's sinking the Titanic. Which one has more thermal energy? You have this object. Sorry, thank you. Got your iceberg. Or this little guy. They are not to scale. That's a huge match.
I call match, bro.
I could have, it's true. But for the sake of this, I didn't. Which one has more thermal energy? Hello? This is him. I know, that's fun that way. Yes. Yes. It is a little one, yeah, like, yes. Oh, yeah. Yeah. Sure, yeah. Sure, yeah, whatever. Sounds good. No worries, but that could have been an email. Okay, which one's got more? Okay, let's talk about this. Which one has a higher temperature?
Oh, the match.
That's an easy answer. So this one has a higher temp. Because you don't care how many particles there are. You just are averaging out all of their energy. So this one's, yes, it's got a ton of particles that are all moving a little bit. This one's got a few particles that are moving aggressively. But because temperature requires you to average out that kinetic energy, having a small number of objects doesn't matter. Yes. I changed the question because you guys weren't saying anything. So this one has a higher temperature. Now I'm going to come back to the original question, Manuel. Just give me a half a second longer. Which one then has more thermal energy?
So sad.
The thermal energy, okay, let's go back to the definition. Thermal energy, the total energy of all molecules in an object.
How big is the iceberg?
That's a normal sized iceberg. It sank the Titanic.
Could have been a toothpick. But you don't know.
Okay, so fine. Let's just move on here. Let's give up on this a little bit. No, I'm not gonna give up. I'm just gonna give you the answer. Yeah. So the iceberg has higher thermal energy. Why? Okay, guys. Yes, Emmanuel, thank you. Because it has so many more molecules than a match does, it doesn't matter that the average energy of those particles are so low. Because there are so many of them, even small contributions from trillions of objects are going to add up to give you more than large contributions from a couple hundred objects. Okay? So this is more massive, which means more particles, which implies a higher energy sum. Is how I'll say that. Yes, Connor.
Better way, or sorry, not necessarily a better way, but what a good way of thinking about it would be like, if you, in a neutral environment, if you have a match and an iceberg, you put them together and you see who wins, would that not be, just have thermal energy kind of
You're trying to melt an iceberg with a match?
Exactly. Who would win, right? The iceberg. So, right? Wouldn't that?
It's true.
Wouldn't that?
It's
work a
true.
little better?
No, well, you're comparing apples and oranges here. You're comparing temperature with thermal energy. You're right. The iceberg is going to absorb a bunch of thermal energy, but how much thermal energy we don't actually know. And different materials absorb thermal energy differently. If you've ever cooked in a kitchen, you know that some materials for pots and pans are better than other materials for pots and pans. Or, more importantly, handles for those pots and pans. If you have has anyone ever cooked with a cast iron pan? With cast iron handles? You don't touch the handles because the handles get as hot as the rest of the pan because iron heats up real well and distributes pretty uniformly. But if you've got an iron pan with a wooden handle, can you grab that handle? Yeah, because wood does not heat up the way iron does, which gets us into what's going on the next page here. So if I was going to heat objects, one is a piece of metal, and the other is a pot of water, which would heat up faster, and why do you think that would be? Sorry? It's the, interestingly enough, the metal pot does not, the metal in the pot doesn't actually, let's assume this. The piece of metal and the pot holding the water are made of the same material. You don't care about the pot heating up. You care about the individual piece of metal, and you care about the pot of water. Which one of those is going to heat up first?
What temperature is the water?
The same.
The water's going to be
They're both starting at the same temperature.
Room temperature.
Sure. It doesn't matter, actually. Which one is going to increase its heat, its temperature, faster?
water goes up faster because the molecules are way more secure because of the state of the
So water conducts faster than a piece of metal?
because the molecules are more secure from each other because of the physical state. So that makes water conduct faster energy.
It's actually exactly backwards. For the exact explanation that you gave, it's actually the metal. So, thank you for giving me the exact correct explanation tied to the exact incorrect conclusion. Piece of metal is going to happen faster for exactly the reasons that Luis outlined. In a piece of metal, we assume a piece of metal is going to be solid metal, the particles are packed more tightly. Because the particles are packed more tightly, they are able to transfer their energy faster. And so they are going to heat up quicker. Because what is heat? Heat is the transfer of thermal energy. So if I ask you to hand something to someone else, what is a quicker way to do that? If you are literally shoulder to shoulder with them, or if they're, 5 or 10 feet away. If I ask you to hand something to someone, Manuel, which is quicker? If you're shoulder to shoulder, or if you have to walk 5 or 10 feet? Shoulder to shoulder. So in a piece of metal where the particles are packed more tightly, heat is going to transfer quicker. It's because, Luis, the molecules are further away in that pot of water. That's why it conducts slower. You are confusing, perhaps.
Because I thought that one of the reasons why we are so sensitive to temperature because we have a lot of water in our bodies.
Yeah, that's true. But if you were made of metal, you'd be more sensitive. Absolutely, yeah. Yes, you would be. So, what we're going to do now is we're going to talk about a bunch of different ways that heat is transferred. And this is, it says here that these are a bunch of demos, but these are not, we're not going to do them as demos. We're going to actually get you guys to do a bunch of these. So, we've got conduction. We know what conduction is? Okay.
Calvin does.
Transfer of energy, like,
It's the transfer of heat.
He specifically.
Could also be in the conversation on thermal energy, yes, but also electricity as well. Transfer of heat through solids, usually, sometimes liquids, or less effectively liquids, I should say, but I'm not gonna. By the collision of molecules.
so we just read of like, what would conduct it faster the energy, water or eraser, for example, because you
Water or
like the energy is going to
no, what was the other object you said?
your eraser.
An eraser, okay.
Because the eraser is made of what is made of this material?
Rubber?
The rubber, and rubber is a terrible
It's a
conductor.
pretty well, it's a terrible electrical conductor. I don't know how good of a thermal conductor it is.
Oh yeah, I am thinking.
Yeah, you're confusing concepts. So what we're gonna do is we're gonna go upstairs here in a sec, and we're gonna look at these two things. I've got a conduction conduction apparatus for you. You're gonna do this one because I've got conduction apparatuses for all of you. Well, I have enough for like groups of 2 or 3. I am gonna do this one as a demo. Number 2 here. Some crushed ice is placed in a large test tube. We're not gonna have time to do this one today. I'll do it tomorrow. A few marbles are gonna be used to keep the ice at the bottom of a test tube. We're gonna add water to that test tube, and you guys are gonna have to tell me whether the ice cube is gonna melt or the water is gonna boil first. That's cool, yeah. Then we're gonna talk about convection. What's convection?
Oh, so that's what my oven does.
Yes, your oven does this. What does it mean for things to be done by convection?
Oh, it's a thing?
Yeah,
Yeah.
a thing.
Yeah.
What's a thing?
Oh, fan. Like it blows in heat.
When like
Keep going.
when heat interacts with a colder temperature, it'll go around and then down and then up again. To the side.
Heat rises in what context? In what kinds of materials? No. Gas is one. Vapor's a gas. Liquids can also heat by convection. But typically we talk about gases transferring their energy by convection. I'm going to do demos of these two as well just because we don't have enough material and I have to light a bunch of stuff on fire for the convection box. And then the last one is
Oh, chill down. I need to see that.
5, 4, 3, 2, 1. The last one is radiation, which is the transfer of energy by electromagnetic waves. This is how the sun heats our planet. There is nothing between the sun and the earth. It's a vacuum. Don't say Mercury and Venus. Yes, of course they're there. But as far as a gas to conduct that energy, there isn't one. It's a vacuum. So how does the sun heat our planet? Well, it uses electromagnetic radiation to heat our planet.
Yeah, and start heating each other really fast, and that produces energy like that.
Yes, kind of. Grab your stuff. I know we've only got 20 minutes left. We're going to go upstairs. Let's go. You need a writing utensil and this handout. Everything else can stay. Writing utensil and this handout. Let's go upstairs.
We're not going to blow stuff up.
No, we're going to hold that up there. And lights up the fire alarm.